Okay, I would like to end the first chapter of the textbook we're following by talking about some applications, right? We've now studied systems of equations. How can we solve them? By representing them as an augmented matrix, taking this augmented matrix, using these elementary row operations, we realize this matrix in its reduced row echelon form. And then once the matrix is in that form, the solution set or the solutions to the given systems are much easier to find, right? And so now that we can do this just in kind of a nebulous setting, right? We're not really applying this to anything. We're just purely looking at the mathematical concepts. Let's see if we can take those concepts to and let them be applied in a physical setting. So I want to start with a chemistry application, believe it or not, and what we can do using systems of equations and solving them in the ways we've talked about is we can actually balance chemical reactions, which I thought was very cool. The first time I learned this when I was an undergrad, I kind of raised my eyebrow and said, well, I know there's math going on when you're trying to balance a chemical reaction, but I kind of raised my eyebrow at like how could this just immediately be applicable? And we'll see that to balance so if you have a given reaction, to balance that chemical reaction, you can rather quickly set up a system of equations. So let's do that. And basically let's look at a specific example. So let me use some smaller font here. So let's consider the following reaction. We're going to look at the reaction SnO2 plus H2 reacts. And then we have Sn plus H2O as the result of this reaction here, where if you're not familiar with chemistry, which I myself am not, I have never taken a chemistry course in my life, even in high school somehow. So, but if that's to speak to how powerful of an application this is, I've never taken a chemistry course, but I can balance a chemical equation because I can solve a system of equations. So here I do know though that Sn is 10, O is oxygen, and H is hydrogen. Okay, and so we know that the number of molecules or atoms on this side needs to be equal to the number of atoms on the other side of the reaction, right? I mean, we don't, during an interaction, this number is conserved. So what we need to do is then balance this equation, right? This means we need the same number of 10 on the left side as we have 10 on the right side. We need the same number of oxygen on the left side as we do on the right, et cetera, right? And so we can set up a system of equations, right? Basically, what we're asking is, if this were to be balanced, what is X times SnO2 plus YH2 to Z Sn plus W H2O. I apologize for running out of room here. And basically the question is, what X, Y, Z, W balances the reaction. Right. What multiples of these terms here do we need so that this chemical reaction is balanced? Well, we can set up a system of equations by going element-wise here. So let's start with 10. For Sn to be balanced, we need the same number of 10 atoms on the left as on the right. And so we would have X on the left, and we would have, right? So we're only looking at things, we're only looking at variables that have, that are in front of 10 here, right? And so we would have X and we would have Z. So for 10, we have that X equals Z. What about for oxygen? For oxygen, we have that, well, there are two oxygens on the left, right? So we would have on the left here, we would have that 2x equals, and then on the right, we only have one. So we need that 2x equals W, right? So that was for oxygen. And then for hydrogen, we have nothing in the first term. Then we'll have 2y equals, and then we have, so we have 2 hydrogen here, 2 hydrogen there, so we'll have 2y equals 2w. So you see how you can set up this system of equations based on just looking at the coefficients kind of element by element. So now we need to solve this system of equations, right? Because solutions to this system will give us when this reaction is balanced. So we can always realize this as a homogeneous system by moving everything to one side, right? So the first equation is x minus z equals 0, and then we have 2x minus w equals 0, and then we'll have, well, let's go ahead and divide by 2 here. Then we'll have y minus w equals 0. What will so now finding how to balance, or finding what numbers balance this reaction, is the same question as what are the solutions to this system of equations? So let's solve it. We can set up our augmented matrix. We have in the first equation, we look at the coefficients, right? So the coefficient for x is 1, and then y is 0, z is -1, w is 0, and then that's equal to 0, right? So we're going to have, looks like we're going to have a 5 by 3 matrix. Then we're going to have 2, 0, 0, -1, 0, and then 0, 1, 0, -1, 0. So this is the augmented matrix that we need to put into reduced row echelon form. And the first thing, right, let's remember our algorithm here. What do we do first? Well, first we need to, well, let's first put our pivot positions so that they're more or less diagonal, right? They don't have to be perfectly diagonal, but more or less diagonal. We can obtain that by replacing, don't know why you're red. Let's interchange row 2 with row 3. This will give us, and for the sake of room, let's just go to the next page here. Row 2 with row 3. So the first row stays the same, 1, 0, -1, 0, 0. And then so I don't make a mistake, let's flip these. So we have 0, 1, 0, negative 1, 0. And then if I remember correctly, we had 2, 0, 0, negative 1, right? 0. Okay. Now our pivot positions are diagonal, right, for the first two rows, but the pivot position in the third row is not diagonal, but that's fine because I know it will be eliminated when we use a row operation to convert that entry to a 0, right? And so that's the next step in this algorithm for converting this augmented matrix into a reduced echelon form matrix. So how could we make this entry 2 here, whoops, sorry, how could we make this entry 0, right? Well, what we could do is we could say row 3 is going to be replaced by row 3 minus 2 times row 1, right? Because we need to have some expression here that takes, once you start with 2, after you apply the expression or the equation, you get 0. So the first and second rows are unchanged. So we have 1, 0, negative 1, 0, 0, 0, 1, 0, negative 1, 0. And then we have row 3, which is 2 minus 2 is 0. And we have 0 minus 0 for the second entry. For the third entry now, we're going to have 0 minus a negative 2. So that's plus 2. And then for the third, we're going to have negative 1 minus 0. So that's negative 1, 0, right? Now, here, sorry, I'm going to kind of snake my way back. This is in almost in row echelon form, right? What's not the case, right? Or what's keeping this from being in row echelon form right now is that the third pivot position here is not a 1. So now we need to take row 3, and we're going to say row 3 is replaced with 1/2 row 3. This gives us 1, 0, negative 1, 0, and then 0, 1, 0, negative 1, 0, 0, 0. I feel like I'm talking in binary almost. You divide by 2, you get 1, and then we'll have negative 1/2, 0. Right? Now, to get this in the form that we want, right? This is in row echelon form. We now need to get it to reduced row echelon form, which means the entries above a pivot position need to be 0, right? The entries above, so what are our pivots, our pivot positions right now? Let me use a different color. I've been using red a lot. I've been using red in terms of what we want to eliminate. I'll use green to talk about our pivot positions, right? Well, the first pivot position there in the A11 or in the 1, 1 spot, there are no entries above it. For the second pivot in the second row, the only entry above it is already 0. For the third pivot in the bottom row, this one, the entry above it is a 0, but we also need the negative 1. We also need this entry to be 0, right? Because we need zeros above and below all pivot positions. So let's do one more row operation to get rid of that negative 1. And I think we can obtain this just by saying row 1 is going to be replaced with row 1 minus row 3, right? Or sorry, row 1 plus row 3, because then we'll have negative 1 plus 1, which is 0. And so after this, we get 1, 0, 0, and then we have negative 1/2 plus 0 is negative 1/2, 0, and then we have nothing changed in rows 2 and 3. So 0, 0, 1, negative 1/2, 0. This matrix is now in reduced row echelon form. right? So this is reduced row echelon form, which is good. This is as simple as we can hope to get this system of equations represented as, right? So we have the system of equations that's now represented as what? Well, what does row 1 tell us? Row 1 tells us that x minus 1/2 w equals 0, which tells us that x equals 1/2 w, right? Row 2 tells us that y minus w equals 0. Sorry. So this was from row 1. This was from row 2, which tells us that y equals w. And then the third row tells us that z minus 1/2 w equals 0, which means that z equals 1/2 w, which makes sense because really, from the start, we knew that x equals z, or sorry, how about here? And then we also knew that y equals w. But now we have all of these variables in terms of w, which means these 3 dots, this means therefore, I don't know how I went back to a bigger font, but so if you see the 3 dots like that, it means therefore. So after we've used our Gaussian elimination here, which is the process of putting the matrix in reduced row echelon form, what we've learned is that w is a free variable. Let's call it a parameter, right? i.e. parameter. So say w equals t, then the solutions x, y, z, w are, well, it looks like we're going to have 1/2 t, t, 1/2 t, and t. And so again, if you'll remember, this is better expressed in terms of pulling this parameter out front as a scalar, which I will do here. And so we can see what the basic solution is. So our solutions here are t, and then we'll have 1/2, 1, 1/2, 1, right? These are our basic solutions. And these are solutions for t, a scalar. So for t and r. And if you would like to look at a specific example, let's look at t equals 2. When t equals 2, we would have the solutions x, y, z. Wow, sorry, that was bad. I mean, my handwriting's bad, but that was a little too bad. X, y, z, w. When t is 2, we would get, looks like we'll get 1, 2, 1, 2, right? Looks like this will be our solution. And so what would the chemical reaction, the balanced chemical reaction look like, right? Then the balanced chemical reaction would be SnO2 plus 2H2. And then we get, I believe it was Sn, and then it will be plus 2H2O. And so this would be your balanced chemical equation from what the chemical reaction that we started with. All right, so this was a chemistry example. I want to do one more example. Let's look at a physics example. Or how about application? And the application that we're going to be looking at is the application to resistor networks. Right? So let's recall a little bit of physics terminology and some values and units and things like this. So let's say we have a circuit here. And I'm going to draw the following circuit. Not perfectly. And a circuit has a voltage source, and these two lines here where you see kind of the break in the circuit, this is our voltage source. And we'll need an indicated direction of current here. So let's go ahead and say, or a voltage, let's say the voltage is traveling in the counterclockwise direction, right? Then, so this symbol represents the voltage source. We have these squiggly lines here. These represent resistors, right? And resistors are measured in ohms. So voltage is measured in volts, believe it or not. Resistors, the resistance is measured in ohms. And then we also have current, right? Anytime you have voltage traveling through a wire or whatever, you get a current. And so I'm going to call this current I sub 1 just because we only have one circuit here, right? In general, like a resistor network could have a bunch of different circuits like we'll see in this next example here. And so this I sub 1, this is the current. And the current is measured in amps, right? So let's look at an example here. Let's say like a specific example. Let's say the voltage source is emitting 18 volts. And let's say this bottom resistor has a resistance of 2 ohms, and then 4 ohms, and then again 2 ohms, like this here, right? So what we know is if we call R, let's say V, R, and I are the following variables. V is going to be the sum of voltage. And I'll just write that these are all going to be the sum of the respective thing, right? So here in this example, I only have one voltage source. So really, the voltage is just whatever that is reading. But for this example, I have 3 resistors, and this capital R is going to denote the sum of the resistance. And so, so we could say sum or total, right? And so this would be resistance. And then I, like I've already said, is the sum of all the currents. In this example, there's only one circuit, so we only have one current. But R here, right? The only thing that would be a non-trivial sum is R is going to be 2 plus 4 plus 2 ohms, which is 8 ohms, right? And a very, very quintessential theorem is Kirchhoff's law. His law simply states that voltage, and when I say voltage here, I'm referring to these totals, right? So it's like the sum of the voltage is equal to blah, but I'm going to drop saying that every time, and I'll just say the voltage. But when I say the voltage or the resistance or the current, I mean the sum of the entire network, right? So voltage is equal to current times resistance. In our variables, this is V equals IR. Now, so what would that mean? Like, let's just look at Kirchhoff's law in our setting here, right? We have a voltage source of 18 volts. And so if these are the same, this means 18 is equal to the current. Like, let's say we're trying to solve for the current, right? Let's do a very basic example of solving for the current using Kirchhoff's law. Well, we're going to solve for the current I sub 1. That's what we're solving for. We don't know what that is. And then that's equal to R, right? or it's times R equal to V. Sorry, I don't know what I was getting at there, but the resistance here, right, we calculated it's a sum, and then it's 8 ohms. So this is going to be Kirchhoff's law in this example says that 18 is equal to I1 times 8 ohms, right? Well, I'll just drop all units for now, and then I'll pick up the proper units here. And this is very easy, right? Here we get I1 is equal to, well, this would be 18 over 8, which should be 9 over 4 amps. So here we can calculate the current using Kirchhoff's law. In general, when you have a much more complicated resistor network here, something more complicated than this, well, then obtaining, like being able to find something such as current from Kirchhoff's law is still relatively manageable, but it's usually not as simple as this example here, right? Because the second you have like juxtaposed circuits, or you know, through a given resistor, you have current flowing in opposite directions. And to speak to directions very quickly here, notice I've specified the direction of my current and the direction that that we're traveling once we leave the voltage source here, right? In this particular example, they agree, right? If you look at where you're traveling, which way the voltage is being emitted, it agrees with the direction of the current. If they were to not agree, so let's say the current is still traveling counterclockwise, but now the emission of the voltage is in the opposite direction, then what we would have written is when you have opposing direction, you pick up a negative. So what this would have said is that negative 18 equals I1 times 8. So direction matters when you're looking at a resistor network or a certain circuit here. So I would like to quickly look at a much more complicated example. I won't go so in depth, but I will at least see how can we set up a system of equations to be applicable to resistor networks here. So please bear with me for a second. Let's draw a network with 4 circuits here. We're going to have a voltage source here. Well, let's start with labeling. We'll start with I sub 1 down here. We'll call this the first circuit with current I sub 1. Then there's a second circuit here, I sub 2, or circuit 2 with current I sub 2, and then et cetera, et cetera. So we have a third and fourth circuit with their respective currents, I sub 3, I sub 4. The current is traveling counterclockwise in all of these circuits. And now let's add in our voltage sources. So let's say we have a voltage source of 18 volts in this direction here. In the second circuit, in the first circuit, let's say we have a voltage source with 23 volts. And then let's say in the third circuit, we have a voltage source of 27 volts traveling this way, and none in circuit 4. Now let's add our resistors. We have 2 ohms here, 3 ohms there, and 1 ohm here, 2 ohms there, 6 ohms in the middle there, 3 ohms At the bottom of circuit 4, 1 ohm between 1 and 4. The bottom of 1 will have a resistor with resistance 5 ohms between 1 and 2. Resistor with 2 ohms. And then I think finally between 2 and 3, we'll have a resistor with 4 ohms of resistance. Okay. So you can see this is a relative to the first example that I covered. This is a relatively complicated network. They can certainly get much more complicated than this. And what we're going to do to set up a system of equations is we're going to write, so let's just write this in words, to set up the corresponding system of equations, we will write Kirchhoff's law for each circuit. Okay. So, and maybe this is implicitly understood, but I should be very explicit right now. The application here is that we are using Kirchhoff's law to set up a system of equations to solve for current, right? I think implicitly I've talked about that we were solving for current, but we are explicitly solving for current here, right? In these examples. So let's start with circuit 1. For circuit 1, Kirchhoff's law says that, and notice, what do we notice? We notice that the voltage for circuit 1 here, bottom left, that the direction of voltage and the direction of current are opposing each other. And for this reason, we will have that negative 23 is equal to, and now we calculate what? Well, we know that voltage is equal to current times resistance. Excuse me. So let's pick a starting point. Let's say bottom left here. And as we travel around this first circuit, this bottom left circuit, what are we going to pass? Well, we have 5 ohms of resistance times I1. So we have 5 I1, right? Because it's always current times resistance. And the current through this section of the network is I1. Now, the next piece of the circuit, if you're following the direction of the current, is to go up this middle here, right? And if we do that, then we'll have 1 ohm of resistance, and then so we'll have plus 1 I1, right? But on this piece of wire, we also have the current I4, right? We also have an effect from the adjacent circuit there. So we have to take that into account. And because the direction of I1 and I4, since those currents are in opposing direction, that means we need to subtract the contribution from I4. So this is going to be minus 1 times I4. And then next, we would go in this first circuit, we would go to the top wire there, and we would have 2 I1, so plus 2 I1. But then notice we also have an effect from current I2, which is opposing I1. So it's going to be minus 2 I2. Minus 2 I2, right? And then, sorry, then the last piece of getting back to where we started is there's no resistance there, right? And so we've now accounted for the total sum, or we've now written Kirchhoff's law for this this first circuit that I've written in green here. And you can see we'll combine terms here, like we have 5I1 plus I1 plus 2I1. We'll combine all that later. For now, let's just kind of maybe see if we can quickly write the rest of the equations here. Now let's look at I2. So if I'm starting here, and I notice the current and the voltage are in the same direction. So that will be positive 18. And then we're going to have 2I2 minus 2I1. 2I2 minus 2I1, because it's a resistance of 2 ohms, and I1 and I2 are in opposing directions. Then, so we've gone here, let's go up. Then we're going to have 4I2, but minus 4I3, because I1 and or I2 and I3 are in opposing directions for this piece of the circuit. And so we'll have plus 4I2 minus 4I3. And then I think the rest of it will have plus 2I2. Whoops. Plus 2I2. For the third circuit, we have a voltage of 27 in the opposite direction of the current. So that's going to be negative 27. And then equals. And let's go around again. Like, let's pick a point, right? So we finished that circuit. I've been starting at the bottom left of all these. So let's start at the bottom left here again. And we go in the direction of the current. And we'll have 6I3, but minus 6I4, since again, there's opposing direction there. So 6I3 minus 6I4. Then we're going up, which will be plus I3. I apologize for the back and forth here. And then we have 3 ohms there. So it's going to be plus 3I3. And then for the last piece of this circuit, we have that resistance of 4 ohms there. So it's going to be plus 4I3 minus 2 or minus 4I2. So we'll have plus 4, plus 4I3 minus 4I2. For the last circuit, let's see. For the last circuit, and again, maybe I'll start here. We're going to have 3I4 plus 2I4. So 3I4 plus 2I4. And then for the third side, we're going to have plus 6I4 minus 6I3. So plus 6I4 minus 6I3. And then lastly, we will have, looks like 1I4 minus 1I1. Plus 1I4 minus 1I1. Okay, and so what we've done, and sorry, what is this one equal to, right? This needs to be equal to some voltage. I got a little bit ahead of myself here. The first 3 circuits all had a voltage source. This one does not, which means this should all be equal to 0 because there's no voltage source, right? So now we have a system of equations in the variables I1, I2, I3, I4. And you could simplify, if you go through the algebra, you can simplify, and I'll go ahead and just write what it would simplify to. It's negative 2I1 plus 8I2 minus 4I3 equals 18. Negative 4I2 plus 14I3 minus 6I4 equals negative 27. And then negative I1 minus 6I3 plus 12I4 equals 0. We have 8I1 minus 2I2 minus I4 equals negative 23. And so this would be now the system of equations that solves for the current. And if you solve this system of equations using our methods of writing this as an augmented matrix, converting the augmented matrix to reduced row echelon form, you will find that, and this would be a very good example to work out on your own, you will get that I1 is 3 amps, I2 is 1/4 amps, I3 is -5/2 amps, and then I4 is -3/2 amps. And so this would this would yield our solution of the currents for this network. And so I think this would be a very good kind of example to, as a self-check, to say, okay, well, I can set these equations up correctly and I can perform the reduced row echelon form algorithm correctly. So this is where I will stop for the applications. This ends the chapter for our discussion of system of equations. It certainly doesn't end us seeing systems of equations. Those will show up through the remainder of the semester, but we're now going to switch gears to focus a lot more on properties and certain rules that matrices have, right? So next, we're going to return to an abstract setting and really kind of discuss matrix theory. We're going to look at matrices and see what kind of mathematical theory and properties and results we can build there. And so that's where we will start tomorrow.